Consider a function f of x that is continuous with no sharp corners over the interval a to b, and consider two numbers, c and d, that are between a and b. In your own words, what is the connection between the slope of the tangent line when x equals c and the slope of the secant line on the interval c to d? Okay, so let's look at a couple of key words here. Consider the function f of x that is continuous with no sharp corners. Okay, we'll talk about that a little bit later, but basically, if there's a sharp corner in a graph, like an absolute value, like the graph of an absolute value function, then when the graph has a sharp corner, the derivative doesn't exist. We'll talk about that later. So what we want to do is, what's the connection between the slope of the tangent line and the slope of the secant line? All right, so let's draw a picture here. Okay, so let's look at a graph. Okay, so let's say I don't know, here's A and here's B, and we have the graph of some function on this interval, maybe something like this. Now let's put C and D here. Let's say C is here, and let's put D here. Okay, so when x is equal to C, here's our tangent line. And that tangent line has some equation, y equals mx plus b. So this is the tangent line. And if we look at the secant line on the interval c to d, well, that's the secant line. Now, obviously, the two lines have different slopes. The way I have this drawn out, the slope of the tangent line is more than the slope of the secant line. But what happens as D gets closer and closer to C? So what about if D was, I don't know, maybe right about here? Oh, I don't want to use blue because the graph is blue. Let's use green. Okay, let's say D is right here. Well, now the secant line looks like this. The slope is different still from the tangent line, but it's closer than the first secant line that I drew. Okay, so what if D gets closer to C? So maybe D is right here. And so the secant line is right there. So now, again, the secant line has a slope that's different from the tangent line, but it's closer to the slope of the tangent line than the green one or the red one. All right. And if D is really close to C, well, now there, that little black one, that's the secant line for the black value of D. So as D gets closer to C, it looks like the slope of the secant line is getting closer and closer to the slope of the tangent line. And that's what actually happens. So let's not use orange here. So we could say as D, this number D, gets closer and closer to C, the slope of the secant line gets closer and closer to the slope of the tangent line. And in our definition of the derivative, our delta x is the distance between the C and the D. So our first delta x was here. Our second delta x was smaller. There's our green delta x. Our next delta x was smaller still, delta x. And our last delta x was right about there, delta x. Okay, so what we're doing is we're taking our formula for the slope of the secant line. which is the difference quotient, is f of x plus delta x minus f of x all over delta x. And so our slope of the tangent line is what happens when, slope of the tangent line, well, that's what happens when this, so we have the slope of the secant line, x plus delta x minus f of x all divided by delta x. The slope of the tangent line is what happens when that distance between C and D gets infinitely small. So as the distance between C and D gets smaller and smaller, the slope of the secant line gets closer and closer to the slope of the tangent line. So we take the limit as the distance between C and D, or delta x, goes to 0. And so there's our connection between the slope of the secant line and the slope of the tangent line.